Welcome everyone to today's webinar, Implementing and Optimizing MIO on AMD Zynq's UltraScale MPSoC and RFSoC platforms. We're happy to have you here as we dive into the critical design techniques and strategies for maximizing the potential of these platforms. Before we begin, let's go over some quick housekeeping items to ensure a smooth experience throughout the webinar. We will have a Q&A session at the end, so please submit your questions at any time through the Q&A button on the control panel. If you need to chat with anybody from our administration team, just send a message through the chat. So, who's Fidus? We were founded in 2001 and Fidus has since grown into a more than 150-person, all North American electronic system design services company. We serve all industries and markets with 3 brick-and-mortar locations, 2 in Canada and 1 in the US in Silicon Valley. We've been working with embedded systems and FPGAs since 2002, and it'd be safe to say that more than 80% of our projects have included FPGA content. We're the proudest of our repeat customer rate, with close to 95% of our customers returning year over year with new projects and new business, a real testament to the quality and efficiency of our work in improving their time to market. We have a strong partner ecosystem, and in fact our partnership with AMD began over a decade ago when we were invited to become their first ever Premier Design Services member in North America. Since then, we've built an exceptionally strong and collaborative relationship, working closely with AMD to support clients, to train on their new technologies like the Versal Portfolio Series or the AMD Embedded Plus architecture, all about helping our customers bring their solutions to market faster. We actually were fortunate to have been named AMD's Partner of the Year this past July. We've been a trusted leader on the Zynq platform since its launch, completing over 50 Zynq UltraScale designs in recent years. From small devices to the largest 19EG parts, we've delivered solutions for applications like storage systems, video streamers, and workload accelerators, using proven schematic blocks, thermal strategies, and reusable code to reduce risk and accelerate time to market. As a full services design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA design, ASIC RTL design, verification, software, hardware, signal and power integrity, mechanical and thermal design. We help our customers by supplying some of the expert skill sets directly, or by managing the complete project from start to finish. So now I'd like to introduce our 2 speakers. First up is Scott Turnbull, the CTO at Fidus, where he's responsible for understanding our client requirements, generating estimates, and leading the advanced tech group here. With more than 25 years of experience in the design services industry, he brings a degree of electrical engineering, unmatched creativity, and technical leadership to Fidus. Joining Scott is Jeremy Brooks, a senior embedded software engineer at Fidus with over 20 years of experience in sectors like aerospace, defense, and IoT. He's got much experience working on hardware platforms, including the Zynq portfolio, making him a key resource for today's session. Now I'll hand it over to Scott to get us started.
Thanks, Alicia. Hello, everyone. First off, thanks for joining us for this introduction to Zynq UltraScale and Zynq UltraScale RFSoC MIO. As mentioned, my name is Scott Turnbull, and I'm the CTO at Fidus Systems. There were 2 main reasons we wanted to do this webinar. One, we've seen multiple clients that are new to Zynq UltraScale incorrectly assign or misinterpret the MIO assignment information. And 2, AMD has created a very large amount of very detailed information and notes to help you understand MIO. And we thought that pulling this information together in one place and talking it through would be valuable in jumpstarting you. Just to let you know, Fidus has completed a large number of Zynq UltraScale and RFSoC designs, so we wanted to share our knowledge. Here's the list of topics we'll be discussing today. We'll start with a very basic MIO talk and then move continually deeper until we finish with a demonstration of the MIO configuration mapping within the AMD tools. Hopefully, after we've gone through all this, you will have an appreciation for the capabilities of the MIO, a level of comfort with how to assign them, and the knowledge that using MIOs is actually relatively simple if you understand some key limitations and if you know where to find the key information. Thank you for joining us today. Let's get started. Let's start off with some high-level MIO concepts. First off, what do we mean by MIO? MIO stands for multiplexed input-output. They're the flexible I/O connected to the processing system of an MPSoC. Just a quick note here though. Throughout this presentation, I'll use the term PS to refer to the processing system and PL to refer to the programmable logic portions of the Zynq UltraScale Plus. The PS is the section that contains the APUs, RPUs, and a large number of other hard functions, whereas the PL is the FPGA fabric portion of the chip. At this time, I also wanted to introduce you to the term EMIO, or Extended Multiplexed Input-Output. We'll talk about that a little bit later. One of the great things about how AMD architected the Zynq UltraScale Plus is that all devices have the same MIO block. Here are the key features of those MIO blocks. In this table, you can see that the MIO consists of a total of 78 functionally assignable pins, which for FPGA folks in the room are split across 3 banks that are powered by user provisionable voltage. Furthermore, although not technically MIO, there are also 4 GTR Gigabit Transceivers with a maximum rate of 6 gigabits per second that are often used in conjunction with the MIOs. Now you can see the large group of hard peripherals that are accessible through the MIO and associated GTRs. Before we move on to the next slide, it is important to note that MIO are not like PL or FPGA GPIO. They're not nearly as flexible. There are more limitations. However, they are attachable to the hard peripherals shown above. Let's dive a little bit deeper. With all that in mind, here's a snapshot of some of the multitude of AMD documentation and apps that I've found most valuable when designing with MIO. Since the Zynq UltraScale Plus is super flexible, the technical reference manual for the device is well over 1,200 pages of detailed goodness. But don't let that intimidate you. You don't have to read all of it, and it is well organized. But certainly read and understand everything that relates to your design. I'll refer to these documents throughout this. With all that documentation out of the way, let's talk about how to start assigning MIO, by first noting my guiding principle of designing with Zynq UltraScale Plus. Simply put, meet as many of your requirements as possible using PS resources. I've seen clients that are more FPGA centric resist this thought, but in the end, I truly believe it is the best way to go. Here are the reasons why. 1, software tends to be quicker to write, implement, and debug than RTL. So leverage software when you can. 2, you'll generally save power using available hard peripherals over programmable logic. 3, the hard peripherals are already there. You're already paying for them, so why not load them up and save the programmable logic for functions that excel from the benefits of programmable logic. For example, FPGA Fabric loves functions that are low latency, highly parallel, extremely high speed, or highly custom. And 4, custom driver creation can be avoided if using hard peripherals to interface to the APU or RPU, whereas custom drivers are often needed for interfacing to PL-based functions. So when we start this off, this is the flow that I recommend. Start with your system requirements, then review and understand what PS hard peripherals are available, then match your requirements to those peripherals and the MIO, and then verify your MIO assignment to make sure that you didn't do something illegal by accident. Let's now focus on the third box, and more specifically, the mapping of functions or hard peripherals to the MIO. So here it is. In my opinion, this is the greatest table that AMD has ever published, aptly named the MIO table at a glance. This table tells you which hard peripheral can be mapped to an MIO pin or a group of MIO pins. Again, this is what I mean by MIO are not as flexible as PL GPIO. Only certain MIO pins or MIO pin groups can be connected to specific internal hard peripherals. It certainly does have good flexibility, but not the extreme flexibility that you're used to with an FPGA. Now that you're all craning to try to see this table, let's zoom in on the table so you can sit back. On the vertical axis, AMD lists all of the hard peripherals that are supported by the MIO. This zoom in obviously only shows a subset of the functions that are available. Now across the top of the table are what I call the MIO identifiers. When someone refers to MIO, one must further specify the exact MIO number of the 78 available that will be allocated to a function on the vertical axis. For example, we would refer to MIO6 or MIO8 or MIO67 to more precisely describe what we're talking about. For now, ignore the weird out-of-order ordinals within the table. So the next step is to drill down to the hardware level to discover how to map MIO 0 through MIO 12 to the actual physical QSPI device on the board. Let's take a deeper dive at implementing this MIO-based QSPI interface. Before we drill down, let's acknowledge that from the table, we see that QSPI peripheral interface can only be assigned to MIO 0 through 12. Now, the weird out-of-order ordinals used to have a mapping function, but AMD has updated the next level tables, so these ordinals are generally no longer required. I suspect they were just left there for historic reasons. So now we know that QSPI interface maps to MIO 0 to MIO 12, but what MIO is what function? To discover this, we have to go into the dedicated QSPI controller chapter of the previously mentioned technical reference manual. When we go there, we find this table. From this table, we see that MIO 0 through MIO 12 are needed for a dual QSPI implementation, and only MIO 0 through MIO 6 are needed for a single QSPI design. For this discussion, let's assume that we're implementing a dual QSPI solution. Honestly, this is now pretty self-explanatory, but to be 100% clear, this table tells us connect chip select for the lower QSPI device to the MIO 5, connect the serial clock to MIO 0, and so on. Then connect chip select for the upper QSPI device to MIO 7, etc. It should be obvious, but for completeness, the MIO number like MIO 5 is not a physical pin or ball number on the chip. It is an MIO number that maps to an actual pin or ball that depends on the actual device and physical chip package selected. This is beyond the scope of the presentation, but it is essentially the same as looking in any datasheet and matching the pin name to the pin ball number. With the QSPI example out of the way, let's look at a Gigabit Ethernet and USB MIO assignment example. Here we return to our trusty MIO table. In this next example, we're specifically interested in implementing one of the 4 Gigabit Ethernet MACs, or GEMs as they're often referred to. Let's focus our attention on GEM 1. We can tell from the table that GEM 1 can only be assigned to MIO 38 through MIO 49. So similarly to the QSPI example, we then refer to the Gigabit Ethernet controller chapter within that same technical reference manual, and we come across this table. This defines the MIO function mapping of MIO 38 through 49 to implement GEM 1. So here we see the typical signals associated with an Ethernet RGMII interface. We're still focused on GEM 1 and see the transmit clock is assigned to MIO 38. Remember, this isn't pin 38 on the physical package. It is MIO 38, which you then map to a specific ball or pin on the package via the datasheet. Moving on, we see TX data 0 to 3 is assigned to MIO 39 to 42. You get the idea. Don't forget, with GEMs, you also have to connect the MDIO, which is the management interface to the PHY. MDIO is comprised of a data and a clock link. Following this table, we can see that if we're using GEM 1, we can assign MD clock and MD data to either MIO 50 and 51 or 76 and 77. I would not mix them. That is, I would not assign MD clock to 50 and MD data to 77. Let's move on to the next example. In this example, we'll be focused on the USB 0 controller, which will be provisioned on MIO 52 through 63. Once again, you rely on the technical reference manual by flipping to the USB controller chapter. Once within that chapter, we see this table that highlights the different USB controller support. In this example, we're going to plan for a USB 3.0 host implementation. Our approach here is to implement the high-speed, full-speed, and low-speed USB capabilities on the MIO. And then necessarily, we have to interface the super speed capabilities to the Gigabit Transceivers, specifically one of the 4 PS GTRs. Here is the mapping table. Don't be confused by the ULPI pin column, since you know that this interface is going to span MIO 52 through 63. So you simply follow the second column, same as we've done before. But what about monitoring the very common power fault signal related to the plus 5 volt bus provision on the USB host interface? Well, that's fairly simple. It's just handled as GPIO type on the MIO. Since we just spoke about the PS Gigabit transceivers, let's take a quick peek at how they are assigned. So let's get started with GTRs. Very quickly, here's the block diagram of the structure of how the PS GTRs on the top right connect to the various high-speed hard controllers within the PS. Like the MIO, the GTRs are connected through a multiplexing system, which affects the overall assignment flexibility. Going to the PS GTR chapter within the technical reference manual, we identified this table as critical to our understanding of how to assign the 4 PS GTRs. The terminology can cause some confusion, but the 4 PS GTRs are identified here with the terminology PHY lane 0 through PHY lane 3, because they're contained within a single bank. But thinking them as PS GTR 0 through PS GTR 3 makes it easy. Just a second ago, we were discussing USB 3.0 superspeed for the USB 0 controller. Here we can tell that we are able to assign the superspeed TX and RX pairs to one of the PS GTR 0, GTR 1, or GTR 2. It's important to note that if we were provisioning the other USB controller named USB 1, our only choice would be to use PS GTR 3. So that lack of flexibility on USB 1 may cause us to favor using USB 0. It's really as simple as that. Here are some thoughts on the other supported GTR interfaces. First off, PCIe version 2.1 root port and endpoint are supported, as well as by 1 by 2 or by 4 lane widths. As per the table, a by 4 configuration would leverage all 4 PS GTRs. All implementations must be matched as per ordinal. For example, PSIe by 1 must use PS GTR 0, aka PHY lane 0. Support is limited to PCIe Gen 2 because of the internal controller's capabilities, but also because the GTR is only supportive of a maximum of 6 gigabits per second, which means that Gen 3, 8 gigabit per second is beyond the reach of the PS GTRs. We previously spoke about connecting the Gigabit Ethernet Max using an RGMII interface via MIO, but you can avoid RGMII, instead use SGMI or 1000 base SX or LX by leveraging the PS GTRs. Perhaps the most common mistake with PS GTRs I've seen is when someone tries to use the DisplayPort source interface. Note the mismatch of ordinals here. For example, DP lane 1 maps to PHY lane 0 and DP lane 0 maps to PHY lane 1. Be very cautious with your mapping, especially on this DisplayPort interface. And really quick before we move on to talking about how to power the MIO banks, it's always important to think about clocking, as these PS GTR interfaces need reference clocks provided as per the AMD table I'm sharing here. Let's now talk about powering MIO. The MIO pins are organized into three banks, bank 500, 501, and bank 502. Each bank has a dedicated I/O power rail, just like how FPGA banks have VCCO or VCC-IO. Here's how to interpret this summary table. MIO pins 0 through 25 are contained within bank 500 and are powered by the VCC PSIO 0 voltage rail. MIO pins 26 through 51 are contained within bank 501 and are powered by the VCC PSIO 1 voltage rail. Lastly, MIO pins 52 through 77 are contained within bank 502 and are powered by the VCC PSIO 2 voltage rail. The user powers the VCC PSIO rails based on the I/O standard they want to support. It is critical to understand that all MIOs within the bank must use the same I/O standard. You cannot assign I/O standards pin by pin. For example, if I power bank 501 with 1.8 volts, then MIO 26 through MIO 51 must all interface with 1.8 volt compatible devices, as it can only drive at LVCMOS 1.8 levels. Simultaneously, I could power bank 502 with 3.3 volts and use MIO 52 through 77 with 3.3 volt compatible devices. So, as you see, your MIO assignment not only needs to consider function mapping as per the MIO table, but it must also consider the interface voltage requirements of the external chips you're interfacing to. Putting all of these details together, here's a schematic snippet from a real-world example of one of our Zynq UltraScale Plus implementations. In this design, you can see some of the most common interfaces assigned to MIO pins. You can also see in the top right the PSGTR assignment in support of USB superspeed. Lastly, I have color-coded the different MIO banks and their associated VCCO PSIO pins to show you that we are cognizant of the voltage requirements that our different MIO pins were interfacing on. In this design, all MIO banks interface using 3.3 volts. We have other designs that utilize different bank voltages. It really depends on the peripherals you're supporting. Of course, it's easier to assign MIO if all three MIO banks utilize the same voltage. However, often you cannot get away with that. Before we complete this section of the presentation with some key takeaways, let's touch very briefly on EMIOs. The concept of EMIOs, or extended MIOs, is leveraged when you have run out of physical MIO pins, but you still want to access a hard peripheral within the PS. In this case, use an internal connection to connect across the PS-PL boundary to utilize a PL, aka FPGA pin, for connectivity. This is a powerful capability, but please understand and appreciate the limitations, restrictions, and in some cases, performance impact associated with utilizing EMIOs. In the interest of time, I'll let you digest the contents of this important table on your own. Now, let's complete this section with a discussion of the most important items we've discussed thus far. As we finish up this section, this slide contains a summary of the key elements I hope you took away from this discussion. Number one, PSMIO is not nearly as flexible as PL or FPGA GPIO. Number two, don't assume anything. Read and understand the documentation. Number three, MIO control signal mapping can be tricky. Make sure you know what you're doing. Number four, as with FPGAs, make sure of your clocking strategy. Number five, pay attention to bank voltage when using MIO. Number six, we didn't talk about this, but I wanted to highlight that different PS DDR memory widths are supported by different package types. Always good to be aware of that. Number seven, the Zynq UltraScale Plus TRM is the most important document for understanding how to use MIOs. And number eight, a small terminology thing, PSIO and MIO terms are sometimes used interchangeably, but technically MIO are a subset of a much larger group of PSIO pins. This completes this section. Next up, just like you use the tools to verify that your FPGA pinout is valid before committing to hardware, I highly recommend you use the AMD tools to verify that your MIO assignment is correct before committing to that hardware. Jeremy Brooks, one of our senior software designers, will now discuss the tools portion of this. Note, Jeremy is a software guy, but FPGA people are equally capable of assessing the planned MIO assignments. Jeremy, please take it away.
Thank you, Scott. My name is Jeremy Brooks, and I am a senior embedded firmware designer at Fidus Systems. I'm going to be going over the tools we can use to configure, verify, and implement the MIO on the Zynq UltraScale Plus platform. Let's start off by looking at how we can configure the MIO using the I/O configuration tool located within the Vivado IDE. For the purpose of this demonstration, we will be using the ZCU102 reference design as it already has a base MIO configuration. In order to access the I/O configuration tool, what we want to do is open up the block design and then open up the Zynq UltraScale block. Once inside the Zynq UltraScale Plus block, we see the I/O configuration tool on the left. Here we see that we have the 4 MIO banks, as well as we can set the voltage level for each bank, as Scott previously mentioned. Down here we see the hard peripherals and how we can configure them. For instance, for the low-speed peripherals, we can look at memory interfaces, and here we find the QSPI peripheral. If we open this up, we see that the QSPI I/O is using MIO 0 through 12, as Scott previously mentioned, and is outlined in the MIO table. Here we can configure various pins. Now we can look at the NAND flash hard peripheral. Now you see here that it is not enabled. If we enable the NAND flash hard peripheral, you'll see that it comes up in red. This means that the MIOs that are dedicated to the NAND flash are being used by another hard peripheral. In order to use the NAND flash in this design, we would have to find the peripheral that's using these pins and disable that peripheral. So for now, we'll leave it disabled. We can go down here and we'll look at I/O peripherals, and here are the hard peripherals that are available. For instance, we have 2 I2C peripherals that are both enabled using MIO 22 and 23 and MIO 16 and 17. We have 2 UART peripherals being enabled using MIO 18 and 19 and MIO 20 and 21. Finally, down here we can see that we have our GPIO peripherals. Currently, we have 3 pins dedicated to GPIOs. These 3 pins are 3 pins that are not being used by other peripherals. If we want to have more GPIO pins, we need to disable one of the other peripherals. For instance, I can disable UART1, and that will free up pins, MIO pins 20 and 21 to be used as GPIO pins, which are fully configurable in this menu. We can look at the high-speed interfaces. Much like the low-speed interfaces, we have our GEM, Gigabit Ethernet. We have our GEM 3 is enabled using MIOs 64 through 75 and 76 and 77. If you see this red conflict view, if it's red, it means we have a conflict in our MIOs and we must change our MIOs. If it is not red, then we are free to proceed with our current MIO configuration. Once we are happy with our MIO configuration using the I/O configuration tools, we can build our Vivado project. We can then use the XSA generated by the Vivado build to verify our MIO configuration using the Fidus IDE. Let's now look at how we can use the Fidus IDE in order to verify our MIO configuration. Using the XSA file exported from Vivado, I was able to create an MIO test platform project within the Fidus IDE. Part of this project will include these files pulled from the XSA, including the psu_init.html file. If I open up this file, I can see the Zynq UltraScale Plus summary report of our configurations. As part of this report is the MIO configurations. Here I can select the MIO configurations, and I can see what each MIO pin has been assigned to, which hardware peripheral it has been assigned to, as well as any GPIO pins that are available, including whether they're pull-ups, pull-outs, in-out pins, CMOS, etc. Here we can verify that our MIO configuration is as expected for the requirements of our project. Once we have generated and verified our MIO configuration for our project, we can now look at how we can control the MIO hard peripherals in software. We will start off by looking at how we can use the MIO pins in a bare metal Fidus project, including how to access the hard peripherals in software. We will then look at how we can access the MIO pins in a Petalinux/Linux project using device trees and standard AMD drivers for each hard peripheral. Let's now look at how a bare metal software project created within the Fidus IDE can access the MIO. We will once again use the ZCU102 sample project we previously built in Vivado IDE using the default MIO configurations. Here we have the ZCU102 platform project in Fidus, which was created using the hardware XSA exported from Vivado. The platform project exposes the hardware to software by providing pre-built drivers and libraries for interfacing with hardware, including the hardware interface configured in the MIO. We can now create an application project which will link into the platform project and provide software with the necessary drivers to control the MIO hard interfaces. Here we have a simple Hello World project which will write Hello World to the UART. This application will use the pre-built UART driver to accomplish this task. If we look at the platform.c file, we can see there's macros which are there to configure the hardware based on the pre-built libraries and drivers. Going to the AMD GitHub repository, we can look at all the libraries and drivers which are provided for the supported AMD hardware, including the MIO hard interfaces. Here, for instance, is the UART PS, which was the UART driver which we used in our software application. Here we provide documentation, the source for the drivers, as well as examples of how the drivers are used. Let's now look at how we can create a Linux/Petalinux project which will allow us to access our MIO configurations via software applications. In this example, we will once again be using the ZCU102 default project which we previously created in the Vivado IDE. Using the Petalinux tools, we use the XSA previously exported from the Vivado project in order to create our Petalinux project. This will import in all the libraries and drivers which will allow our software application to use the MIO interfaces. This is done when Petalinux automatically creates the device trees. Each MIO hard interface will have an entry in the device tree. These device trees will associate the basic drivers with each device, allowing software to access the device through the default drivers. In the case of GPIOs, we can use the sysfs interface to access the GPIO. This concludes our presentation on implementing and optimizing MIO on AMD's Zynq UltraScale Plus MPSoC and RFSoC platforms. We hope this webinar provides you with a clearer understanding of how MIO can be used to meet your project requirements. At this point, I would like to hand back the presentation to Alicia.
Welcome everyone to today's webinar. Okay, hello everybody, and thank you for being here. I'm just going to ask Jeremy and Scott to jump onto their camera feed, and we will start with the Q&A. So just a quick reminder to everybody that is here, if you have any questions that you'd like to pose to Scott and Jeremy, just make sure you pop them down in the Q&A button down there in the bottom. Okay, so first question here, either of you can answer if you don't mind. So there's a question here. You mentioned that MIOs are less flexible than PL/IO in terms of mapping. Can you elaborate on how one should prioritize or balance the use of hard peripherals versus programmable logic for optimal performance?
Yeah, sure, Alicia, I'll take that one. So really, I go by my guiding principle, which is use the PS MIO when you can. If it doesn't meet your requirements for speed, for flexibility, for voltage levels, anything like that, then I would go to the PL GPIO. But generally speaking, I always prefer using the PS MIO first, and then to the PL GPIO to sort of round out what I'm doing.
Excellent. Okay, thank you. Okay, another question here. Given the complexity of the technical reference manual you mentioned and other resources, what sections or key tables would you recommend focusing on if I'm a first-time user of Zynq UltraScale Plus?
Yeah, I'll do that one too.
Okay.
So really, it's really well organized. Like, yeah, it's 1,270 odd pages, but it's really well organized, and it's organized in a structure of hardware peripheral controller. So, there'll be a section or a chapter for your GEM controller. There'll be a chapter for your USB controller, and so on for all of them. So what you want to do is you wanted to read the first few chapters, and then you just really concern yourself with the peripherals that you're using, and then just go chapter by chapter. So, you end up probably having to go through, 200 pages of the 1,200. But over time, since we've done all sorts of different designs and stuff like that, I've kind of been through the whole thing now. But yeah, don't be intimidated by it. It's really well written, and the tables are like the key to everything in it.
Thank you. Okay, I have another one here. As projects scale and you require additional peripherals, how can designers plan their initial MIO assignments to allow for future expansion or changes?
You want that one, Jeremy, or you want me to grab it?
No?
Okay, I'll take it.
Okay.
So if you load up your MIO first, then you'll limit some of the future capabilities that you have. But let's take I2C as an example. So you've got two I2C controllers in there, I2C0 and I2C1 within the PS. So what I would do is I would load up I2C0 as much as I can. So if I had 4 devices on my I2C bus, I would use them all with I2C0 as long as it meets my requirements. And then I would leave I2C1 unused. So then that gives me future options to do stuff with I2C1 controller, whether it be through the PL GPIO as what we discussed as EMIO or the extended MIO, or through the dedicated PS pins later on. But I wouldn't just, I've got 2 controllers, so I'm going to put 2 devices on I2C0 and 2 devices on I2C1 because I can. And your software guys will will be happier with you if you load up one controller rather than using both of them.
Jeremy, is there anything that you wanted to add to that?
No, I think Scott handled that quite well. Thank you.
Okay. Okay, question here. Could you share some examples of projects where optimizing MIO assignments led to significant design or performance improvements?
I can handle that one. So I've worked on several projects where we've had to optimize the MIO configuration in order to meet our system requirements. One example would be where we had to enable the ice. We had a QSFP harness that needed to be configured using I2C, and we couldn't use the regular I2C bus, so we had to enable the MIO in order to configure this harness and allow for the optical connection to enable. Another example would be where we had to have both the QSPI and NAND flash working on a particular board, and we then had to enable the NAND and disable some of our other peripherals in order to get this system up and running the way we wanted. Ultimately, the flexibility of the MIO interface is quite useful depending on what the requirements of the project are.
That's a great example. Thank you. Okay, well, it looks like we don't have any more questions right now, so I think we're gonna close it out. So thanks, Scott. Thank you, Jeremy, for your time. I hope that everybody found it valuable. We will be sharing this adding it to our website fairly shortly. If you have any questions or would like to chat with one of our experts about starting your project with Zynq or perhaps migrating from Zynq to Versal, just jump on our website at fidus.com and fill in the form there, and somebody will follow up with you straight away. Okay, thanks everyone, and have a great day.